Katia, for the invitation, and thank you, you and Canute, for organizing this seminar that has been very important for the community, especially in these COVID times. So this is, I took a very heavy task. I mean, I cannot really do it, how to give a survey of the Calderón problem, what has happened in the last 42 years, but I will just be a personal journey. And I apologize if I don't refer to your paper. There are many contributions I'm not going to mention. Especially, I'm going to just talk about dimensions 3 and larger, essentially. And so there are many important results in 2 dimensions that I'm not going to cover. That's another talk. So the Calderón problem, I will go very quickly because I think most people here know it. The problem is, can you recover the conductivity of a medium by making voltage and current measurements at the boundary? It's called electrical impedance tomography, also electric resistivity tomography in the geophysics literature. And the reason why it's called Calderón problem, because he proposed it he gave a mathematical clear formulation of the problem. His motivation was geophysical prospection to find oil, because oil has a very different conductivity than the surrounding rock. It's also been proposed as a possible method combined with the mammography for the screening for early breast cancer detection, because the conductivity of normal breast tissue is very different than the cancerous. The reason is blood is very highly conducting, and the tumor needs blood to grow. This is Calderón, of course, a famous analyst of the 20th century. His contributions are enormous. The Calderón sigma theory, uniqueness of the Cauchy problem, the Calderón projector, many others, interpolation, Calderón by Lancourt theorem, etc., etc. But he published only 1 paper on inverse problems, and he thought about this problem. This is his personal recollection when he was an engineer working for the oil company of Argentina in the late 40s, but he didn't publish his result until 1980. One of the current applications of EIT, there are many, is to continuous monitoring of the functioning of the lungs. This is in a hospital. There's a COVID patient, because there is a very different conductivity on the lung if one of them has collapsed or has problems because the blood is not going through and so on. And the important is that you can monitor it continuously, as opposed to CT scan or MRI that you have to take the patient to do this. And it's portable, can be used for different patients. And another recent application has been, a proposed application has been the imaging of a stroke with EIT. Here is like you have an inclusion or a different conductivity inside the brain. There is an hemorrhage on the right, and there is a clot on the left, and the conductivity is very different in both cases. However, the symptoms are very similar. So you would like to distinguish quickly, for instance, in an emergency ambulance, which one it is, because the treatment is completely different. And this is, we have started the mathematical work on this, and these are some of the pictures with simulated data. Again, it's very good for contrast. EIT will never give you very high resolution. And what is done in that paper is essentially do like what we do in an X-ray, go around, and you see how the conductivity is varying. There is an hemorrhage on the right one, and there is a clot on the left one, and it's homogeneous in the first one. Yeah, I was watching, because of my family history, I was watching a video about a concentration camp in Poland, and they suspected that there were, they had pits built on the ground to throw the bodies of people that the Nazis had murdered. And this is the method that they used to do it is EAT.
The scientists now deploy another scanning technology known as electrical resistivity tomography, or ERT.
So this box, connected to our array of 81 electrodes, will measure the resistivity of the ground along the entire length of 40 meters to a depth of 6 or 7 meters.
The control unit, powered by an electrical car battery, fires hundreds of electrical pulses through the metal spikes into the ground. It measures the way soil conducts electricity and creates a map distinguishing natural soil and man-made disturbances.
I'm not seeing any video.
There is an eyewitness.
I'm not seeing any video.
You're not seeing any video?
There is audio, but no video.
Oh, that's strange. I'm watching it.
I think you have to share your whole screen and not just the window of your presentation.
Oh, okay. Let me see. So how is that?
You might have to unshare, and then when at the time of sharing again, you'll choose to share your computer screen instead of the presentation window.
Well, this in the consideration of time, let me just tell that they use EIT to find whether there were pits, because the conductivity in the soil is very different if you have a pit or a rock and so on. I thought it was interesting to see this, but you can take a look at the YouTube video. Maybe when you want to watch it later, you can see the video. Okay. So very quickly, the mathematics of the Calderón problem, the current is by Ohm's law is given this way. The conductivity is the inverse of the resistivity, and there are no currents of flux, no sources of sinks of current. And then you put the voltage potential on the boundary, and you measure the induced current flux in the normal direction, the current in the normal direction. And the Calderón problem is very easy to state. Does knowledge of this map determine the conductivity? Of course, this is an idealized problem, and you would like to, of course, discretize this problem when you can get a good approximation. So I will start with Calderón's problem because that was the motivation. What he did was to linearize the problem at constant conductivity, say 1, and then he obtained that this is a linearized problem in the direction of a function h. So you look at the Fréchet derivative in the direction h. For every function, for every harmonic function, you're taking just conductivity 1. And the question is whether you can recover h from all this information. And he simply took these exponentials, e to the x rho, e to the minus x rho. The rho is a complex frequency. The length of the real part is equal to the length of the imaginary part, and they are perpendicular. And so you plug it in, and you obtain the Fourier transform of h for every c non-zero, and therefore you recover h since h is an L2 function. So the Fourier transform is known almost everywhere. And this is very simple. So these are the analog of waves in this case. It's exponentials. Of course, this is not it's an elliptic equation. We don't have the standard waves, but there are exponential decay in some regions, exponential growth in some others, and also oscillations. And the first result was by Kohn and Vogelius. And I heard in 1983, they proved that knowing this map for a smooth conductivity, you can recover all the derivatives at the boundary. And I heard a talk by Bob Cohn and MS Araya. Was at MS Araya at that time, the whole year. And we started work with John Sylvester on this problem. So the uniqueness that we proved was for C2 conductivities. And this is the uniqueness result, and has been extended in several ways. This is, again, does not include all the results. Let me point out the last ones, which are generalization where you have only one derivative in some sense. This is Haberman proved for dimensions 3 and 4, W1n means one derivative ln. And Carroll and Rogers proved for all dimensions bigger or equal than 3 for Lipschitz conductivity. This is important because that's a very reasonable set of conductivities. And the conjecture is that W1 in dimension 3, dimension 2, of course, this is known for even less regular conductivities at infinity by the result of Staller-Paparinta, that this is optimal for uniqueness, but nobody has produced a counterexample with conductivity having less than one derivative in some sense. And the conjecture is, you assume something more a priori, like which is reasonable in practice. I believe that the uniqueness is valid for piecewise smooth conductivity. The result here of being conormal was an attempt to do that, but we could only get conductivities in C1 plus epsilon, so not all piecewise smooth conductivities. And the construction method was done by Adrian Nachman and stability by Alessandrini. And several numerical methods have been developed, maybe several authors, some of them joined. I cannot write all of them and all the papers on this. So this is a very brief summary of some of the results. The reason why you need a regularity here is that the methods that have been used, you do this reduction to the Schrödinger equation by making this transformation. It has some advantages in the sense that you can consider a general potential now, but has the disadvantage that for the conductivities, you're taking two derivatives. So the less regular the conductivity, the more singular the potential. And that's the difficulties using this transformation that we may not need to do. In general, you can define the Dirichlet-Neumann map as long as this problem is well posed for any complex potential Q. And that's the problem that one considers. So it's more general, but we solve that problem, you solve the conductivity problem, and you simply prove what has been called Alessandrini's identity, integration by parts, Q1, U1 is Laplacian U1, Q2, U2, Laplacian U2. So it's linear in Q on the left, the non-linearity is in the products of solutions of different equations for Q1 and Q2, and it's linear here in the difference of the Dirichlet-Neumann map. Again, the non-linearity comes from U1 and U2 restricted to the boundary. For instance, for uniqueness, and you can use the same for stability or reconstruction, you get this equation that the product of solutions is orthogonal to Q1 minus Q2. And so inspired by the work of Calderón, we constructed solutions, waves. Again, it's an elliptic problem, and this is the analog of waves that behave like Calderón solutions for large complex frequencies. These are complex frequencies, so that rho or rho is equal to 0, so these are harmonic functions. That's the reason to reduce it to the Schrödinger equation, because this is a perturbation from the Laplacian. There is another contraction I will mention, I will use it later. Suppose you take this complex frequency so that rho or rho is equal to 0 and have the real imaginary part, and you take and they are perpendicular, the real imaginary part that have the same length. So you can take the plane generated by the real part and imaginary part, then you can construct solutions of the equation that are concentrated near the plane. So this is the case for large rho, but the A rho, the support decays to the plane, and this plane changes with the rho. And for the conductivity equation is this, yes. So, but these are solutions concentrated near planes. It's analog to what one does for Gaussian beams, is constructing solutions near geodesics. And then you can prove this result very easily using this. You take these solutions, the other ones, that's not the original proof. The original proof is you reconstructed the Fourier transform again, but here you cancel completely the exponentials and you take rho large, and then you get the Radon transform of the difference of the potential and therefore the potentials. So there is a connection between EIT and the Radon transform, as well as with the Fourier transform. And so this is the application. Lambda Q determines Q. So this implies that the Dirichlet-Neumann map for the conductivity determines the conductivity. An important example is where you can apply this result for the potential is in optical tomography. One takes light instead of currents. And so this is the diffusion approximation. This is the density of photons, the diffusion coefficient, and the optical absorption. And this is mathematically is the same as the previous problem. It can be reduced to the previous problem. The physical interpretation is different. And since Q in this case will be complex, if omega is non-zero, you can recover both the diffusion and the absorption. If the frequency is zero, you can recover one of them. And optical tomography is used to monitor the brain on very small babies that were born prematurely, because there are small brains and then the light can penetrate better than in large objects. Okay, so I'm going to jump to 20 years later or so and consider the partial data problem. So that means, which is of course important also in applications, you only measure on part of the boundary. So the support of F is contained in one open set, and you're measuring the Neumann derivative in the other open set. And the Calderón problem with partial data, that's knowledge of this map, determines the conductivity in omega. And this is an open problem that new ideas are needed for this problem. So some of the results, if the conductivity is known, and the two sets are the same, but this is the most important case, in fact, and you assume that you know the conductivity near the boundary, then you can recover. And with Koenig and Sjostrom, we show that you take a point outside and you shine light. You consider the front face where it is illuminated and the back face. So you measure the Dirichlet data in a small neighborhood of the complement of gamma 2, gamma 1, and then the Neumann and the complement. And then you can recover. But then here you're making measurements everywhere, either the Neumann derivative, the current, or the voltage. But the point x0 can be arbitrarily close to the domain. For instance, if it is a convex domain, can be as small as you want. Isakov consider again the case when the two are the same, but the complement of this set is part of a plane or a sphere, because he could construct these complex geometrical optic solutions, CGO solutions, by reflection. Okay, and part of the proof with Koenig and Sjostrom was the construction of nonlinear phase functions. The ones we had before were linear, and this is the phi and psi real value, and the remainder goes to zero, star goes to infinity. An example of a limiting Calderón weight. I'm not going to describe this in detail. Is the log of x minus x0 when x0 is a point. That's the reason why, we take this point outside. And in order to find these phase functions, the gradients have to be perpendicular of the real and imaginary part as before, and the length has to be the same. So this is a system of PDEs, complicated system, but can be solved in this case. And for this phi, you can actually construct the side using the distance function from this vector to the sphere. You can solve the transport equation, I mean the amplitude, by solving this equation, because this is perpendicular to this, and they have the same length. This is the Cauchy-Riemann equation in the plane generated by the gradient of phi and gradient of psi. And the other important point is that in the region that you don't know, which is called the boundary omega plus here, where the gradient phi of the normal is positive, you can estimate with the corresponding weight the normal derivative in terms of the solution, and this the case for tau large. So this gives control of this part, because you need this to be strictly positive to have this control. And so that's another key ingredient in the proof. I'm not going to give all the details. But this is a limiting Calderón weight. So this is the reason for considering limiting Calderón weights. And you need that phi and minus phi be a Calderón weight. That's part of the problem. And this has been, these are called complex spherical waves because the level sets of phi are spheres that starts at points as outside. So you're probing the domain with spheres centered at the point x0, and that has been used by determining inclusions, obstacles, etc., using the enclosure method developed by Ikehata for different type of problems, conductivity, Hertzsprung, elasticity, Maxwell, etc. So the reason why these are useful is you take a point x0 aside, you take a spherical wave, this conductivity jumps, and because of the reflection, you are going to be able to determine where it jumps and how much it jumps. That's the reason that these are useful to determining inclusions and other anomalies. Okay, so now I go to the anisotropic case. I'm doing a very quick summary of the local problem. This is the conductivity, it's a metric, but the definite muscle tissue is anisotropic, and this is the induced current flux in that case. And this is an interesting obstruction to non-uniqueness. So you can prove that you take a change of variables, which is the density at the boundary, you take this new conductivity, which is called the push forward, the Jacobian transpose, composed with gamma, composed with Jacobian divided by the determinant, gives rise to a new conductivity that gives you the same measurements. If both of them are isotropic, then psi is identity, and then you can recover uniqueness. But in general, this will be anisotropic when you do this change of variables. And it's very simple because the equation is invariant under transformations. You change u to the inverse. And the open problem, and I'm going to single it out, is the only obstruction. Okay, so it's a large element of non-uniqueness. The question is whether that's the only obstruction to uniqueness. And this is a geometric inverse problem. You can, for the people interested in this, you can consider compact Riemann manifold with boundary, Laplace-Beltrami operator. In coordinates is given here. G upper J is the inverse of G. The conductivity is related to the metric. The conductivity and metrics are related. One is the inverse of the other. G upper J is the inverse of the metric G. You can consider the Laplace-Beltrami operator and boundary data F. And this is what's called the conormal derivative. The Dirichlet-Neumann map. It also arises in holography. Can you see the three-dimensional world, for instance, in 2 dimensions? And so the inverse problem is formulated this way. Can you recover the bulk? It's called the bulk, the manifold, and particularly the metric. From the Dirichlet-Neumann map is called the boundary 2-point function. It's an important problem in holography. And the only thing that we really know in this generality, there are some partial results in another direction, is these are real analytic, connected, compact. It's real analytic, that's the main assumption. You can measure it anywhere in the open set, that you can have partial data. Then if one metric is called the pullback of the other, for conductivity it's called the push forward. So one can prove this, that's the only obstruction in this case. And in fact, you don't need to know the manifold, you just need to know the boundary and the Dirichlet-Neumann map. But there is a big assumption here, which is real analyticity, which of course is not satisfied in many important cases. Some another non-unique results that are very interesting were done by these authors. When you're measuring the same set, gamma is smooth all the way in the interior, but only hurled up to the boundary, not smooth up to the boundary. And then it's not true that this is the only obstruction. And this is based on Miller's counterexample for unique continuation. There is a result for second-order equations in divergence form. You can have u and the normal derivative 0 in the boundary and u not be 0 in the interior, as exactly under these conditions. It's only Hölder continues up to the boundary. It doesn't have even one derivative. And if they are disjoint, there are counterexamples when gamma is, these sets are completely disjoint, gamma is smooth up to the boundary. But it's also based on this Miller's counterexample. So the open problem, I already mentioned it, but this is, I want to emphasize it. If you have two conductivities and an isotropic, they have the same Dirichlet-Neumann map, is it true that there is a diffeomorphism, which is the identity of the boundary, so that one is the pullback of the other? And it's only known, as I mentioned, in the real analytic case. Okay, I have been hitting my head on the wall with this problem for many years. I don't know how many years, try many things. A new idea is needed. Maybe it's not so difficult with a new idea. And I encourage people who have not tried to see whether they can do it. I don't want to take this problem to my tomb. I offer $1,000 for anybody who can solve this problem. I don't have $1 million like the Clay Institute. But somebody asked me whether it was $1,000 for every dimension. No, it's $1,000 for all the dimensions.
You need to adjust that for inflation.
Okay. I will do, at the moment, let's just say 1,000. Okay. So this was a summary of some of the, of course, I cannot cover everything, it's impossible. That has been on. Again, I apologize if I did not refer to some of your work. And I saw already a typo here. This is for nonlinear elliptic equations. So now let me go to this decade. There has been a lot of progress in recent years about inverse problem for nonlinear equations in general, and my emphasis here will be in elliptic equations related to Calderón's problem. And the general theme has been that the nonlinearity helps. This was observed first in the hyperbolic case, in the paper with Slava Kurilev and Mati Lazars. We use multiple linearization in the sense that look at several interaction of waves. Initially, we use 4, and then in other works we use all the linearizations. And in the elliptic case, this was done for the first time by Mohadi and Oksanen in 2019, and Lazars, Limaitanen, Lee, and Salo, again using multiple linearization. The second order linearization has been considered before, but higher order linearization in this generality now. So for the conductivity equation, which is the main topic here, is again, I'm not mentioning all the results. I think the first result is due to Sun using linearization method that was initially proposed by Isakov for nonlinear parabolic equations. We did the case when gamma is anisotropic. Again, this is gamma depending on X and U. For the anisotropic case, we use second order linearization. Hervas and Sun have results when gamma depends on X and gradient U. And the case when depends on U and gradient U has been done here. First, let me consider the semilinear case, simple semilinear case to explain the idea. It's easier to explain. For instance, let's take this case, use to some power. Then for a small enough f, there is a unique solution of the Dirichlet problem. And then we also consider the partial data for this problem. Now, and gamma 1 and gamma 2 are arbitraries. And the result obtained with Katia, and then there was another work all at the same time by these authors. One can prove for any open set, gamma 1 and gamma 2, that Q1 is equal to Q2. So this is in contrast what is not known in the linear case. Again, the nonlinearity helps. And it has been generalized in the same paper to more general potential, not just Q times the power. And let's, for instance, let's take a case of power 2. And in this case, you take solutions of this form. Again, we're going to consider second order linearization. If you have higher powers, you have to consider higher order linearization or a general potential, all the linearizations. And then when you, the important thing here is that the linearization is just the Laplacian. And then when you obtain an identity, I'm not going to derive it completely here, the Q1 minus Q2 times the product of 3 functions, but these are all solutions of the same equation. It's not like before when you have products or solutions of different equations. Okay, and then we use a result obtained with Dos Santos Ferreira, Koenig, and Shostran, that the span of this product, when the functions are 0 on the complement of gamma 1, is dense. So this is generalization of what we did for the Calderón problem, the local problem. Here you have, this is the realization of what Calderón did. You have solutions, product of solutions, but the boundary value on part of the boundary is 0, and this can be arbitrary. And this is dense. And using this result, we obtain that Q1 is equal to Q2. So this is the advantage of the multiple linearization, because you obtain solutions of the same equation. You're linearizing around the same function. And these are the same solutions of this. They're all harmonic. Laplacian is 0. Okay, so this is the main result for general. When you have full data, we can take a conductivity, depends on U and the gradient U. By the way, there are conductivities that are nonlinear called varistor resistors. This is a nonlinear resistor made of semiconductors. So it's a physical problem in some cases, and then you can define the Dirichlet to Neumann map this way. And the theorem obtained was Katalin Karstea, Ali, Faiz Mohammed, always have problems, Faiz Mohammadi, and Kian, and Katia, is that in this case we have a uniqueness. And this is a general result for general conductivity. Of course, you have to be analytic in U and the gradient of U. So we can do the multiple linearization. So these are powers in U. The nonlinearity consists of powers of U and powers of the gradient of U. And let me quickly explain the idea of the proof. You develop in Taylor series around 0. And then you have this k times. So this is the case differential of this function, which I'm assuming is holomorphic. So we have a power series. This is convergent power series expansion and can be written this way. So to prove the theorem, this involves derivatives of the conductivity. It's enough to prove that all the derivatives are the same at 0. This is the x, you don't need an erraticity in x, you need an erraticity in U and the gradient of U. And then the result follows from something similar that I mentioned before. Here is not the product of solutions, but the product of gradient, very similar to what you have with the Calderón, and the divergence of gamma 0 gradient Vga is equal to 0. So the span of this set is dense. And this is proved using it's explicitly stated in this paper of Krupsik, Lassas, and Siltanen, and it's based on the same ideas as in Sylvester and that paper already mentioned. And why is this useful? Because when you do the multiple linearization, again, we're going to take just m equal to 2. So this is just the second order. I'll just explain for the second order linearization. You get the products of 4 functions solving the derivatives and gradients of 4 functions solving the conductivity equation. And then we need to prove that this function is 0. But here, what you can use to explain the ideas here, you can use solutions, CGO solutions concentrated near planes. So you get the products concentrated near planes, and in another plane, they intersect in a line, and you take a point in that line, any point, it can be arbitrary, and then the amplitudes of the solutions in the CGO are concentrated near the point in particular. I'm giving a very, very rough idea, but this is the main point, that you have 4 here, and we use this to conclude that t is equal to 0 and therefore solve the problem in that case. For partial data, we don't know the result in general. Only in the case that the dependence on the gradient depends on only one derivative, or a directional derivative. Here. Again, you have the assumption of holomorphicity in this in the gradient of U and U. And now you take any non-empty set and you measure in the same set. The support is containing gamma. You measure the Dirichlet Neumann map. And you take a constant conductivity because that's the solution of the equation. You assume that this is a solution of the equation. So when this is 0, and so if you have the Dirichlet de Neumann map the same, then the conductivities are the same. And this can also be applied to conductivities of this form. As far as we know, this is the only result for nonlinear elliptic equations where we have partial data. As I mentioned before, we don't know this problem for the linear conductivity. And it's another example where the nonlinearity helps. And again, you reduce the problem to prove, again, the completeness question. The question is when you take the multiple linearization, take the men's order linearization, you want to prove this. It's reduced to the problem of showing that certain products of gradients or solutions in this case is orthogonal to F. You want to prove that F is 0, and then you have to prove that that's dense. And in this case, the functions here are harmonic with this support containing gamma, because we assume we are doing the linearization along the constant conductivity, say 1. This is the linearization here around the conductivity 1. And so this is, again, is this theorem that we prove with Katia, where the products of gradients of solutions or harmonic functions, they have the support contained in a subset of the boundary, arbitrary subset on the boundary. This is dense. That's the essential result that we use. Of course, it's more complicated when you take M-order linearization and all that, but that's the main point. We don't know this density for other equations. I mean, we know it for Laplacian plus potential when the potential is analytic, but not in general. Then if you could do that, you could generalize this result as well. This result on partial data. An open problem for both cases for this partial data or for the general conductivity that I mentioned before. For this problem is the anisotropic case. That will be interesting problem to try. Okay. There are many references of inverse problem for nonlinear elliptic. I don't mention nonlinear parabolic or certainly nonlinear hyperbolic. This is partial list of some of the results for many different types of elliptic equations and so on. So it has been a very active field. So the last topic in the last 10 minutes or so that I have is inverse problems for non-local operators, in particular the fractional Laplacian. And also this opens an avenue for considering more general non-local operators. So we consider the fractional Laplacian, which usually is defined in terms of the Fourier transform. And this is, of course, is non-local operator. So that's why is it useful? Because this involves values of the fractional Laplacian involves values of u far away. It's a convolution. So you can get information from many places. And so the non-locality also helps. That's the topic of this part. And the fractional Laplacian arises in superdiffusion. For instance, the normal diffusion is the heat equation. You take the steady state of this, you get the fractional Laplacian. Several people have considered the time fractional. This is not what I'm going to talk about here, but it's also an interesting inverse problem. And there are several results on this. This is a survey. There must be many new results on this. This is a survey from 2015. Okay, so to pose the problem, because this is non-local, you cannot just give it directly data. You give data in the exterior. So in Sobolev space HS in the exteriors, and you look for a solution U in HS, and you can prove that you can solve this exterior problem. In probability theory, this usually represents a certain process. So we are going to observe the process outside, and we would like to recover the process inside. That's the inverse problem. So given this Dirichlet to Neumann map Q, can you recover Q? And the first result, although not the first one published, took 4 years to get this published. You take two open sets in the exterior, arbitrary open sets, can be as small as you want, as close to the boundary as you want. You take a function supported in one of them and you measure it in the other one, doesn't matter whether they are disjoint or not. And for this, doesn't matter the dimension. Then you can recover the potential. So they have local data for arbitrary open sets and for every dimension. We don't need to separate two and higher dimensions like one does for the usual Calderón problem. And one of the main tools is that this theorem, which is you take a distribution in H minus R, can be quite singular, and this is the fractional Laplacian restricted to an open set, and that's 0. U is 0 in that open set, and the fractional Laplacian is also 0. Then U is identically 0. This is a very strong unique continuation result, because this is not true for the local case. When S is equal to 1, you can have a compactly supported non-zero function, and U and the Laplacian are 0 outside the support, and U is not 0. And this is, one uses the Caffarelli-Silvestre extension. The square root of the Laplacian is known to be the Dirichlet to Neumann map in a half space. So what they do is, so that the fractional Laplacian appears as the boundary value of that. And so when S is equal to 1/2, so you extend the dimensions by 1. This is called the Caffarelli-Silvestre extension. S is equal to 1/2. This is just the normal derivative. Very easy to show in the upper half plane. And then in general, you get this factor 1 minus 2s, which can be singular. It's not a uniformly elliptic equation. It's a degenerate elliptic equation, and then this is has a weight, and then you prove Kaldeman estimates and unique continuation for this type of equation. This is Caffarelli-Silvestre extension is very useful for fractional Laplacians, because it reduces to an elliptic equation but degenerate. Okay, and the implication for this is that any L2 function can be approximated by solutions of the fractional Laplace. This is not true for the standard Laplacian. Harmonic functions, for instance, when Q is equal to 0, are not dense. You have an infinite dimensional complement. And you apply this to the identity that is exactly the same as in the case of Calderón problem. I mentioned that one of the main topics of this lecture is to show that the products of solutions, products of gradients, maybe many of them are dense. And this is the same here, but now we can prove it because you can approximate any function with solutions of the equation. And so this proves that Q1 equal to Q2. So let me finish. We mentioned a recent result. We're trying to solve the anisotropic problem, analog of the anisotropic problem. First, we consider a case of a connected, a smooth close, like a torus or a sphere. in dimension bigger or equal than 2. You take the positive Laplace-Beltrami operator, and we can define the fractional Laplacian as in terms of powers of the eigenvalues. These are the eigenvalues, and these are the eigenfunctions. This is the orthogonal projection on the eigenspace of lambda k. This is essentially Fourier series on the manifold. You have eigenfunctions and eigenvalues. Now here you don't have boundary. You take an open non-empty set, and we want to solve this equation. So alpha is between 0 and 1. And this has a unique solution if you are orthogonal to the kernel. The kernel are the space generated by the constant function. The constant functions are solutions of the equation. And so, and then you can define you can actually write down the solution in terms of Fourier series again. And then you define, here we don't have boundary data, as I said before, the source to solution map. So you have an F supported in the open set. This can be very small. And you measure the Dirichlet to Neumann map, which corresponds to the fractional Laplacian in the same open set. So this is the fractional and isotropic Calderón problem in this case. That's the knowledge of this, and you know O, and the metric in the set O, which is arbitrarily small, and you recover the manifold globally. So this is the source to solution map. So this is F is the source, and this is the solution in the open set. And the theorem, of course, there is an obstruction to uniqueness. If you have a diffeomorphism, so that one metric is the pullback of the other, and phi in this open set is identity, then the source to solution maps coincide. So the question is that the only obstruction? And it is the case. And this is the theorem. You take two smooth close connected Riemannian manifold dimension bigger or equal than 2. And these open sets, and suppose they are the same, and you make the source to solution maps are the same for all F, so that they are orthogonal to that the integral is 0, in other words, and there is a diffeomorphism, so that one metric is a pullback of the other. And this diffeomorphism in this open set is identity. So this is one of is maybe the only case I know, an elliptic problem, inverse problem, where you can recover the metric unconditionally. And again, the non-locality helps. And I don't have much time, but let me just explain the main steps in the proof by using the measurements, which are the source to solution map. You can prove that the heat kernels are the same. In the heat kernels in this open set. And then we show that if you know the heat kernels in the open set, then it's true. So you reduce it to an inverse problem for the heat equation. Then there is a diffeomorphism having the properties that you want. And to show this, one reduces the problem to the wave equation. There is a method to go from the heat equation to the wave equation, and uses the result of Belychev, Kurilev, and Tataro that have solved the problem for the wave equation. So the reason why you can recover the heat equation is because of the representation of the fractional Laplacian in terms of the heat equation. And we show that from here you can recover all the moments of the heat kernel. I cannot go through the proof now, but this is just by integration by parts. You apply it to the nth power of the metric, and then you integrate by parts many times, and you get the difference of the heat kernels is orthogonal to, here you get this, is orthogonal to eventually you prove to all the powers and you get all the moments of the difference of the heat kernel, therefore they have to be the same. Let me finish with that, just to say that there are many other results. An important one is the variable coefficient one, where you have Laplacian of a metric, for instance, plus a potential. You can recover the potential. In that case, you know the metric, you can recover the potential, and we don't know the result for the local problem. There are many more results, and I cannot mention all of them, but let me finish with this. Thank you.
Thank you very much, Gunther, for the very interesting talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself.
No questions, nobody could follow anything?
Professor Uhlmann, I have a question. No,
Yeah,
can I
good.
ask a question?
Sure.
Oh,
Who
thank
is
you.
this?
In page 15.7, you have said the heat kernel is related to wave equation.
Yes, yes.
I want to ask why they have the relations.
Okay, so let me, I didn't have time to explain that. Thank you for the question. So this is the heat equation, the wave equation problem. That was the wave equation.
Okay.
Okay, and the reason is there is this formula, very nice formula, this transmutation formula of Kanai was done in 1977, that you can relate the heat kernel e to the minus t pj to the wave kernel. This is the sign, this is the wave kernel.
Okay.
So once you know this, so you can go from one to the other. You can invert this, you can invert some Laplace transform and go from one to the other. It's a very useful, this is for uniqueness, right?
Yes. Thank you. Thank you very much.
Yeah, I didn't have time to explain that, but
Thank you very much. Are there any other questions or comments, please? Any other questions or comments?
I cannot hear. Sorry? I cannot hear. Katya, can you tell me what the question is?
I cannot hear either. Sorry.
It was someone's mic was on accidentally. There was no question.
Oh, I see. Okay.
Okay. Are there any other questions or comments?
Hi, Gunther. This is Anna. Very nice talk.
Thank you.
You mentioned the magnetic Schrödinger operator. So I was wondering, in general, for systems, nonlinear systems.
Yeah, for nonlinear systems, let me see. For the case of the wave equation, I know the hyperbolic equations. I know the elastic system, for instance, has been considered. That's the main one. For elliptic problems, I don't think this has been done, as far as I know.
But do you think that's something similar under maybe condition on the eigenvalues or?
Yes. You mean for this type of problems?
Yes.
Yes. I think you can generalize this to, you can try systems, for instance, first to consider the isotropic problem, as it will be interesting. And system is the next one, for instance, elastic system.
Right.
The elliptic problem.
Yeah, right. Yeah.
The hyperbolic problem has been looked at and has been solved, actually. But not, and also for the hyperbolic case, Einstein's equation has been considered on many systems, Young-Mills equations. But for the elliptic, I think we are behind.
Thank you. Wonderful
Yes,
talk.
very good question. Thank you.
Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Gunther. Once again, thank you very much.
Yeah,
Thank
yeah,
you. Thank you
you're
very much,
welcome.
everyone, for coming. Thank you.
Yeah, thank you.